Welcome everyone to the Condensed Matter seminar. Our speaker, Lyndsey McMillon-Brown, comes to us from NASA Glenn, where she leads a program of research on perovskite-based photovoltaics for space applications. She's going to tell us about that today. Lyndsey did her undergraduate work at Miami University in Ohio and her doctoral work in chemical engineering at Yale on material design and nanopatterning for improved solar cell light harvesting. Lyndsey is also engaged in important efforts to promote diversity, equity, and inclusion in our fields and in outreach. At Yale, she co-founded the Society of Women Engineers grad chapter. And at the IEEE Photovoltaics Specialists Conference, she's created an event with a great name called Minority Carriers. You can read some of her insights on this work in a recent commentary published in Nature Energy earlier this month. So Lyndsey, we're delighted to have you here. Welcome, and the floor is yours.
Thank you. Hi, everyone. I'm really happy to be here with you guys today. I'm going to share slides. Okay, I think you guys can see my screen. Thanks for the thumbs up. I appreciate that. So again, I'm Lyndsey McMillon-Brown, and today I will be discussing perovskite-based photovoltaics for applications in space. So NASA's Artemis program has plans for our return to the moon with a human lunar lander that's going to explore the lunar South Pole. So we also have Gateway, a multi-purpose outpost to orbit the moon and support the long-term human return to the lunar surface. So from Artemis, we hope to gain new experiences on and around the moon, preparing us to send the first humans to Mars in the upcoming years. In addition to being an ambitious and exciting project, Artemis is also going to require a lot of new technology. So NASA's approach is to define planetary science missions that are of great interest for knowledge gaps, and then from those mission requirements, the agency determines the strategic gaps. So those strategic gaps identify what technology needs to be invented so that we can perform the desired planetary explorations. So for any PIs that are listening, if you're interested in conducting research with NASA, I would recommend you take a look at the Lunar Science Report and the decadal surveys. The decadal survey is conducted once a decade. It looks out about 10 years into the future. And in that, they prioritize research areas, observations, and like hypothetical missions that would be required to make those observations. And each of these reports identify technological gaps, which are opportunities for researchers to work with NASA. So for Artemis, it's been realized that we're going to need a lot of power. And specifically when we're considering lunar surface power, we need very large arrays at significantly reduced cost. So we think these goals are more readily met by perovskite thin films. Here's the team of researchers helping me with this project. We have focused primarily on materials development, device synthesis, and increased stability and durability for the space environment. Our external collaborators are University of California, Merced, specifically Professor Cy Ghosh, and the National Renewable Energy Lab, where we work with Joey Luther. So the name perovskite applies to this structure of the material because the perovskites for photovoltaics take on the same structure as the perovskite mineral. Solar materials with perovskite structure are commonly hybrid, organic, inorganic, lead or tin halide based material. And the structure has a generic form ABX3, where A and B are cations and X is a halide. A popular mixture so far in the field consists of methyl ammonium iodide and formamidinium iodide mixed with lead iodide. But there are many different alloy potentials, and perovskites have a lot of favorable properties that make them enticing for space applications, including their really thin films. The active layer is around 250 nanometers. They're radiation hard, and what that means is after exposure to proton or electron radiation, they still have a high remaining factor and the devices still perform fairly well. They're defect tolerant, which is particularly special when we consider the current state of the art for space, which are crystalline silicon or crystalline gallium arsenide based solar cells. Due to their crystallinity, any vacancies or defects in their lattice will result in reduced device performance. But perovskites are a bit more tolerant to any errors in their lattice. Perovskites are also liquid or vapor phase processable, and we appreciate that ease of manufacturability. It gives us some options and flexibility there. They can be flexible literally when you deposit them onto flexible substrates, and they're lightweight, especially when you can get rid of a cover glass or encapsulant. They can also be low cost, and later I'll talk about their tandem opportunities. However, perovskites are not without their own challenges. They have challenges that we have to address. Not all of the layers currently in a perovskite solar cell device are suitable to withstand the harsh environment of space. Specifically, these perovskites struggle a bit with vacuum and thermal instabilities, as well as moisture and oxygen sensitivities. The moisture and oxygen sensitivities, however, those concerns disappear when we put a device in space. So we do believe that all these challenges can be overcome with significant materials development. So to achieve a cell that can endure the space environment, we're exploring materials that should improve lifetime. Specifically, we're searching the material space for efficiency, manufacturability, and durability. So we have high confidence this can be achieved by exploiting some exotic alloys. So it's already pretty well accepted that methyl ammonium lead iodide has a high efficiency and a lower durability. There's some concerns with the durability because it can generate a structural phase transition at about 55 C. They are susceptible to moisture-induced degradation and some thermal stability issues. Also, light-induced trap states can form, and some halide segregation can happen in the mixed halide perovskites. Formamidinium lead iodide has a higher durability, but tends to have a lower efficiency. And unfortunately, this pure FAPI lacks structural stability at room temperature because it can crystallize into the photo-inactive non-perovskite delta phase, which is also commonly known as the yellow phase, or the ideal black phase is very sensitive to humidity. And then when we consider cesium lead iodide perovskites, they exhibit high thermal durability, but a lower efficiency. And fully organic cesium lead bromide has really good thermal stability, but it's not an ideal, it doesn't have an ideal band gap. Cesium lead iodide has a more suitable band gap, but it crystallizes also in the yellow phase at room temperature, and the black phase tends to only be stable at much higher temperatures, like temperatures above 300 C. So all of that together, we're working to design a material that's suitable for space needs, and we need that solution to be right in the middle, optimizing efficiency, manufacturability, and durability. And we know that solution is going to be an alloy. So when you're designing a solar cell, there are a lot of layers that we have the freedom to change, and the selections that we make for each of those layers is going to impact our final output. And we have expectations or goals for each layer. For our absorber layer, we want it to have a high broadband absorption, long charge carrier lifetime, and defect tolerance. For our transport layers, our whole transport layer and electron transport layer, we want them to be highly conductive, of course, charge selective, and inert to the absorber. So we're not really messing with the chemistry there and decreasing the efficacy of our absorber. We want our contacts to have high conductivity and also to be inert. We don't want them to dope our absorber layer, and we don't want them to oxidize. Your ideal substrate is going to be transparent, flexible, and lightweight. I have on this diagram here FTO, which is fluorine doped to tin oxide. That's a chemically inert charge selective contact. And ideally it would have high transmission, good conductivity. And really we use it because it promotes adhesion for the subsequent deposited layers. I have on the bottom here a simplified band diagram, and that really gets at the internal device physics. But in short, we have a photon of energy greater than or equal to the band gap that's absorbed. We excite an electron from a lower energy state to a higher energy state. And then charge collection is then guided by the energetics of the cell, which lead these electrons to the cathode and holes to the anode, because other routes are just energetically unfavorable. So as we design these cells for space, we're making materials changes from the terrestrial cells in hopes that the end result will be a more stable and high performing cell. So when we determine how great our solar cell performs, there are a few critical figures of merit that I'd like to review first. So the efficiency of a solar cell is the ratio of the energy output from the cell to the input energy from the sun. The energy output from the cell is determined as the maximum power point, which is the product of the cell's open circuit voltage, short circuit current, and the fill factor. When we look at the current voltage or the IV characteristics of a solar cell, the short circuit current is the current through the cell when the voltage across the device is 0. It's the maximum amount of current that can be extracted from the cell. The open circuit voltage is the maximum voltage available from the cell, and that happens at 0 current. So using the open circuit voltage and the short circuit current, we can determine the fill factor, which is the shaded region shown here. And that's the ratio of the max power from the solar cell to the product of the open circuit voltage and the short circuit current. Graphically, it's the measure of the squareness of the curve. And this is helpful for us to quantify like any impact of parasitic resistance within our cell. So if you look at a cell with significant shunt resistance, we would have an IV curve that looks something like this. Shunt resistance is typically due to manufacturing defects that cause power losses by providing an alternative current path. And this diversion happens and it reduces the amount of light generated current that flows through the junction, and therefore we see a decrease in voltage. Your series resistance would look something like this, and that mainly reduces your fill factor. So series resistance is generally caused by internal resistance between the absorber and the contacts, or resistance of the contact itself. So the aim of this work, funded by the Space Technology Mission Directorate Early Career Initiative at NASA, is to develop a perovskite solar cell that could be space qualified. And the American Institute of Aeronautics and Astronautics has space qualification specifications that all solar cell technology needs to meet before it can be flown in space. But these standards were derived for wafer-based technologies, specifically silicon and gallium arsenide-based cells. So we're using them as our starting point here, but space qualification is really related to mission requirements. So I have a book chapter that's under review, Prospects for Perovskites in Space, in a book that will be titled Photovoltaics for Space. And in that, we call for new standards specific for thin film photovoltaics that are going to operate in space. And so on the ground in the lab, while we perform tests, we're really conducting multifaceted ground-based tests that relate to the natural environment that these cells will see. That includes their thermal performance, atomic oxygen exposure, UV radiation.
Yeah.
I think we have another open mic.
You'd be open to the stuff.
Radiation of electrons and protons, and vacuum stability. So really, I'm considering low Earth orbit and lunar conditions for this work. To begin, we took high efficiency candidates that are leading the research space in terrestrial perovskites. And I seek to determine how do these cells perform in thermal stress. So if you remember the optimization Venn diagram, we're really focused on durability in these studies. So we're looking at these architectures that were developed from previous work funded by the DOE, and we're varying the topmost layers here shown in these NIP device schematics. And we want to see what's the best whole transport layer contact combination for cells that have metal oxide electron transport layers. So in this case, our active layer is a triple cation perovskite whose device architecture is shown. And we're going to expose these cells for 24 hours to 100 degrees C. It's generally accepted that Spiro and PTAA are not very thermally stable, so we don't have too much high hopes for these. But we would hypothesize that the PTAA, the device shown in the middle, would probably be our best performer because the organics content is kind of encased in metal oxides in this device. So in the first case, we took this unencapsulated device with a spiral whole transport layer. And on the right, I have pre-stress versus post-stress efficiency distributions. So we're surprised, but they survived the thermal stress. And we see about a 50% power conversion efficiency loss. And upon closer inspection, we realized that the short circuit current remained largely unchanged. The open circuit voltage dropped marginally from about 1.1 volt to 1 volt. And again, the greatest losses we observed were actually in our fill factor, and that's symbolic of reduced efficiency in extracting our charged carriers. In the second case, we're looking at an unencapsulated device that has PTAA and molybdenum oxide with an aluminum electrode. And this one exhibited some degradation in power conversion efficiency, but it performed really well in this thermal stress test overall. And this was the one that we had hypothesized would probably do the best. And again, that organic material is kind of encapsulated or shielded by the metal oxide and aluminum. In our final case, we took this unencapsulated device with PTAA and a gold electrode, and we observed that it lost also about 50% power conversion efficiency, but it did survive the thermal stress test. So this really gave us a bit of pause because we anticipated that these organic layers would flop fairly quickly. So we realized they're a bit more durable than we give them credit for, but we also acknowledge that we're going to need a lot more than 24 hours of thermal stability for our applications. Now we expand on this test by taking baseline solar cells and expose them to thermal 75 degrees C and vacuum 10 to -6 torr stress conditions for 24 hours. And we also observed degradation here. On the left, I show the device architecture. In the middle is a pre-exposure IV curve showing about 17% device efficiency. And on the right, I have post-exposure. So on the y-axis is the percent difference in the efficiency, and the x-axis is sample number. So you're looking at discrete samples here to kind of get a feel for what we observed. In this test, the organic inner layers again, were a little bit more favorable than we thought they would be. So we're seeing some decrease in performance, however, and we selected 75 degrees C for this preliminary investigation because that's been a reported solar cell operating temperature in low Earth orbit. So again, we're using these relevant conditions for our tests. So the takeaway here is that our baseline MAPI device with organic inner layers does survive our thermal and vacuum stress. Now, we want to take a closer look at these results and really determine where the losses are occurring. So here we're breaking down short circuit current, open circuit voltage, and fill factor figure of merits for each discrete sample that went through this experiment. And again, we're seeing largely our short circuit current remained unaffected or even marginally enhanced. Our open circuit voltage drops slightly, but really the killer is our fill factor. And from this, we can conclude that that thermal vacuum stress is damaging the transport layers. And as a result, we're introducing internal resistance into the cell. So we're really interested in more stable materials for perovskite cells for these space applications, and we're eyeing metal oxides as transport layers. Now, the goal is to develop a fully inorganic cell focusing on that efficiency, manufacturability, and durability. And most of these transport materials in terrestrial perovskites are organic, and they're really unlikely to meet the AIAA S111 outgassing standards for implementation in space. So as a solution, we want to replace those with metal oxides, and they're earth abundant, they improve durability, they can reduce costs, and they can expand our manufacturing options. So the next thrust of our work that's still ongoing is studying the merits of replacing these organics with metal oxides. So we're benchmarking the electrical performance of our devices, and we're conducting durability tests to determine the metal oxide's effectiveness. And the metal oxides we're interested in include aluminum oxide, titanium oxide, copper oxide, and similar materials because they have high electrical conductivities. They even may offer protections to our perovskites, slowing the perovskite degradation. And this is a current direction that our lab is taking. So I'll have to report those findings at a later date. But if there's anyone in the room whose interest I happen to have piqued and you'd be interested in collaborating, we'd love to talk. So I want to shift gears a bit and share some recent results from our lab on how these materials endure exposure to moisture, because I mentioned earlier that's another challenge point. And we're still focusing on durability here. So when exposed to humidity, the perovskites' hygroscopic amine salts decompose, and that results in device degradation, fairly significantly so. And AIAA S111 standards require passing a 95% relative humidity test at 45 degrees C for 1,500 hours. And these standards actually are meant to be representative of the time a solar cell will spend on the ground prior to launch. So we studied low outgassing, two-part space qualified silicone encapsulant, DC-93-500, and we wanted to see what's its ability to protect perovskite cells from moisture. So we took a perovskite methylammonium lead iodide active layer and encapsulated it in DC-93-500. And here I show a series of transmission spectra over time for these perovskite films that were encapsulated. We started time equals 0, right, as made, and then subsequently measured periodically after they were exposed to an hour chamber, 30 degrees C and 95% relative humidity up to 880 hours. There's no detectable change in chemical stoichiometry of these encapsulated samples. I can say that because we don't see any new features arising in the transmission spectra. So from that, we can conclude that there are no changes after 880 hours of damp heat. So at this time, at 880 hours into the experiment, we randomly selected 2 samples from this experiment and sent them for a flight test. This is where it gets real exciting. So we used the Materials International Space Station Experiment, MISSY, to send to our perovskite sample for exposure to low Earth orbit by external mount on the International Space Station. This gives us an opportunity to see how these cells perform as they interact with all of the kind of characteristics that make up the space environment. That includes ultraviolet radiation, atomic oxygen, ionizing radiation, vacuum, and thermal cycling. So we have really good facilities for ground-based testing, but it's so valuable when we can see how all these things play together at once. And so we took 2 samples from our moisture stability experiment, and one flew outside of the International Space Station on MISSY for 10 months, and the other was a ground-based control, which means it traveled to Texas for integration, and then it traveled back to us to stay on the ground. So it did almost everything the MISSY sample did except go to space. And I have the timeline of the sample shown here, where it was integrated into the MISSY platform on ground in October 2019. It launched in March of 2020. It returned to Earth in January of 2021, and it was back in our hands in March of 2021. So let's take a closer look at this sample. On the left is a photograph of the sample in the MISSY holder after the flight. And the inset is also a closer photo of the sample post-flight. We were already excited when it was returned to us and it was still black. That's a great indicative that it's the photoactive black phase of perovskite. So that was a great, kind of canary for us. So the sample was aligned in the zenith direction on the International Space Station, which means it was generally pointed towards the sun. And the MISSY flight facility holds these samples in an aluminum frame that has a fairly large heat capacity. So that kept the sample slightly warmer during the eclipse period of the orbit than that would happen if they were maybe away from a spacecraft body and allowed to radiate into the deep space. So for that reason, our samples saw a minimum of about -20 degrees C and a maximum temperature of 85 C. So on panel B, I'm showing a edge-on photograph taken with a digital microscope. So the arrow on each image is aligned with where the encapsulant and the perovskite film are, and glass substrates are on either side. So the brown on the bottom image is actually a borosilicate substrate that darkened due to the UV exposure during the space flight. So images C, D, and E are photographs of the sample that were taken. The first one, image C, right after fabrication, so time is 0. D is 290 hours into the humidity experiment, and then figure E is post-flight. So from this, we can acknowledge that we don't see any visible new spots that were created due to space flight. And panel F is transmission data from the MISSY flight sample, and black is the as-made device and red is post-flight. And there's a relative drop of about 30 to 40% transmission intensity broadband. And this reduction is expected actually because our substrate was not selected for optimal radiation tolerance. So we opted for borosilicate substrate because it's more easily sourced, and it's favorable for our deposition protocols of the MAPI ink. However, we would want to use a space qualified glass, something like a ceria-doped borosilicate in future flights, and that glass would be less likely to darken. So here I want to briefly compare the flight sample on the bottom and the control sample photos on the top, and each are really largely unchanged across the timeline of the experiment. So here we're looking at confocal fluorescence images of our samples being excited by 430 nanometer light. And you can see on the ground control there, or on each sample actually, there are dark regions that don't emit. But the density and the size of the non-emitter regions are different between the ground and the flight sample. And on panel C and D, we're looking at histograms generated from PL maps. So panel C is mapping the central emission peak energy in electron volts, and panel D is summarizing the charge recombination lifetime. So if we look at these, we see the MISI sample overall has a higher energy and it's blue shifted, but the MISI sample also has a slightly lower lifetime. So when we take this data together, we summarize that the MISI sample has a higher density of small defects, which explains why the lifetime is a little bit shorter than the ground control, but the energy blue shift is typically indicative of dissociation into methyl ammonium and lead iodide, but we don't see any lead iodide forming in the film. So at this point, we're still unsure entirely where this blue shift that we're observing is coming from. Now, here we can explore the stability of the samples and how they behave. And this data was taken with constant illumination over the course of 15 hours. So the illumination was broadband. And in the case of the data shown in green, that was broadband with a cutoff at 575 nanometers. So we selected that cutoff because blue and green light are known to speed up the light-induced degradation in perovskites. So this will elicit a worst-case scenario response. Also, the excitation wavelength in the other data falls within this region, so this range might help us to get at why we saw that blue shift. I want to mention that this analysis was done by our partners at UC Merced and Professor Sai Ghosh's lab. In panel A, we see that the ground sample shows an initial fast drop in the PL intensity, and then it stays flat. So, but conversely, the MISI sample is recovering. We can see in both the green and the red curves. And actually what we're watching here is the defects in the film forming, but then they're actually being annealed through light soaking over time. So this is the light-induced healing of strain-induced defects that we're witnessing over this 15-hour experiment. Now in panel B, we take a look at stability we see from the MISI sample. So the ground-based control data in black shows a response that's pretty typical for perovskites actually. They slowly blue shift over illumination because the lead iodide is generated over time. So you would start to see that sample film yellowing. And we actually observed yellowing in the ground sample, but not with the MISI sample. The flight sample, its energy is not shifting, and neither is the width of its spectrum. So it's really a very stable material. And in panel C, we're taking a look at the full width half max, and that's a measure of the amount of defects in the sample. So if we see a narrow full width half max, we would say our material has fewer defects. So the film's emission is closer to its pure band gap. And our ground sample is a bit bizarre here actually, but the flight sample is the more ideal performer. So overall, from this analysis, we conclude that the MISI sample is more stable and it exhibits light healing, and we see no lead iodide formation. So here's some photographs comparing the flight sample to the ground-based control after that light soak. And again, you can see that the control sample is, showing that mustard yellow color. And after we let it rest for a bit longer in the lab, it went full yellow, so it's lead iodide right now. But the MISI flight sample is holding strong, still the desirable black phase. So here I want to share some temperature series, temperature dependent PL data, and our excitation wavelength was 532 nanometers. And at each temperature, we're plotting the entire spectrum. And the ground control sample here shows that at about 148 Kelvin, we're jumping to the higher energy emission. And this right here is evident of a transition from tetragonal to orthorhombic crystalline structure in the perovskite. Now, the Missy flight sample shows that transition happens at much lower temperatures, actually at about 55 K. And this value of 55 K is much lower than any transition observed in the literature. Typically, perovskites make this transition anywhere between 150 to 130 Kelvin. And if we look at both samples, the peak emission energies for each sample is about the same at about like 1.68 EV, I would say. But the flight sample is still a lot more stable. Now, this is desirable because the tetragonal structure is ideal for photovoltaic devices because power conversion efficiencies are much better than that of a device that's made from orthorhombic crystalline structure. So our takeaway here is that the Missy flight sample shows much lower phase transition than typical. And we're starting to really feel that the presence of all those small defects on the surface of the Missy flight sample might be helping to stabilize the material. And the material itself actually seems to have be better for after having gone to space, which was not what we expected, but it's wonderful. So here we're going to take a closer look at the largest visible defect on the sample, which is shown on the top right in the post-flight image of the film. So on the bottom left panel, we have a confocal image of that spot. And from here, we actually learned that this isn't just a hole in the film. In our lab, we were calling it the hole for a while because we didn't think anything would be there. It's not a hole, but there's actually some perovskite crystallite structures within that region. So then we took scanning confocal spectroscopy of the same region. And in panel B, we're taking a look at the intensity of those emissions. And the intensity, the dark ring, means we have a very little light emission from the edge of that hole. And the rest of the film, however, and even some of those crystallites within the hole are still emitting. And when we take a look at that emission energy, which is shown in panel C, this reveals that whatever is emitted from that outer ring is blue shifted to the orthorhombic perovskite energy emissions. And the red emissions correspond to the energy level appropriate to tetragonal. So altogether from this defect, we learned that in this region, the edge is actually held to that orthorhombic phase, but the internal region is still tetragonal and it performs normally. So this gives us some promise that even in the instance of defects or voids, the void won't be fully photoinactive and we'll still have some regions that are performing. So we have learned a great deal from this Missy 13 flight sample, and we expect to be learning even more as we've just launched a suite of samples on Missy 15, actually, and we're delivering samples for Missy 16. So these flight opportunities provide us great support to our continuous materials exploration and the development for enhanced stability in these devices. So here I have some pictures of the SpaceX Dragon spacecraft, which left on its 23rd cargo resupply mission to the International Space Station, and perovskite solar cells were on board, and we were really elated to watch this launch in late August. So I'd like to switch gears a bit and kind of do some forecasting for the field. And I really think that there's great potential for perovskite tandem devices. Single junction power conversion efficiencies for perovskites have already reached about 24%, and they have radiative efficiency limits at the low 30% range. So the combination of exceptional photovoltaic properties and tunable band gaps in a wide range and low temperature processability really make perovskite materials attractive for multi-junction tandem cells. And it's anticipated that we could easily achieve about 30% power conversion efficiency with tandem devices. And they have radiative efficiency limits of around 42%. Now, wide bandgap perovskite top cells and low bandgap bottom cells can include another perovskite, or crystalline silicon, or copper indium gallium selenide, or CIGS, bottom cells. And these are all suitable materials towards realizing the goal of low-cost tandems that would also be suitable for operation in space. And on the bottom left, I have an image taken from a paper published by Lang et al. And here they have generated perovskite SIG tandems, and they perform at 15% in AM0, which is the solar spectrum in space. And they retained actually 85% of their initial power conversion efficiency during operation, while they expose these cells to about 68 MeV protons. So on the right, I have an example of a 2-terminal silicon perovskite tandem cell, and this was generated by Oxford PV. And Oxford PV currently holds the record efficiency for silicon PV tandems, since they have a device that was certified at NREL with an efficiency of 29.5%. So we really need to establish a strong understanding of perovskites and specifically their operations in space before we develop tandems for long duration operation in space. But in the future, this is the direction that we would like to take. And there exists great promise for these tandems, but there are also a lot of opportunities and necessary advancements that need to occur. So I'd like to focus on some of those advancements here, and they include understanding and mitigating the tendency for these metal contacts to dope the perovskite or undergo redox. And also interface layers need to ideally be defect free and compatible with the process methods of the rest of the device. So really I'm thinking of solvent compatibility here, which is quite a challenge when you're making these cells. And we also need to have the appropriate band alignment. Similarly, our recombination layers need to have low optical and electronic losses, and they need to exhibit solvent compatibility to processing techniques and be stable. The active layers of these devices can sometimes fall prey to ion migration and phase segregation and environmental induced decomposition, like some of the things we've been talking about today. Particularly when you break down these junctions, the low band gap bottom cells are based on a mixed tin halide perovskite or another material like silicon or SIGs. And when the low band gap material is a perovskite, it's typically tin films which suffer from instability due to easy oxidation of the tin. And this can result in a shortened device durability and poor stability. Now, in the case of the wider band gap cells, these are usually achieved by substituting bromide for iodide and iodide-based perovskites, and that higher bromide content will widen the band gap, but then those suffer from defects and photo-induced phase segregation. So whenever you're layering so many constituent materials, there is just deep concern for energy level mismatch, which can also be a source of loss in these devices. But the majority of the challenges that I've mentioned here are materials issues that can be resolved through material selection and engineering. And there are a lot of developments that are currently being made in these areas daily. When we think of these specifically as they pertain to space, we need to keep in mind radiation hardness and vacuum and thermal stability. And we're feeling quite motivated that this is attainable by looking at the results of our MISSY 13 sample. So to conclude today, I'd like to remind you of the key takeaways. We have a MAPI terrestrial baseline device with organic inner layers, and it survived a thermal vacuum stress. The results from that was the short circuit current was largely unaffected. Our open circuit voltage dropped slightly, and the fill factor really was the major killer. And from that, we could conclude that our perovskite devices with the metal oxide transport layers will likely be most stable in space relevant environments. So we're working on developing those. Our MAPI device, our MAPI film, encapsulated MAPI film survived 10 months in low Earth orbit, and it exhibits great thermal and illumination stability greater than that of its ground-based control for reasons that we're still exploring. Finally, looking towards the future, long-term, there'll be great potential for perovskite tandem devices for space missions, be it perovskite silicon, perovskite SIGs, or perovskite perovskite tandems. I would like to again acknowledge and thank my collaborators at the University of California, Merced, Professor Cy Ghosh, and at National Renewable Energy Lab, Dr. Joey Luther. I'd like to thank NASA's Space Technology Mission Director at its Early Career Initiative Program for funding this work. And I'd like to thank you guys for your attention, and I'd be happy to take any questions.
Great. Well, thank you for that very nice overview of this exciting work. So I guess we'll go over to questions. And I see there's already 2 questions. So let's start with Kimberly.
Hi, Lyndsey. Thank you so much for your talk. It was really interesting. I'm working on thin film deposition, and when looking at your diagrams, I was kind of scared because I would imagine it's hard to balance the thermal expansion coefficients and especially with the thermal cycling in space. So how did you go about beginning your research? Did you look at thermal expansion coefficients, or did you look at other properties first?
Yeah, that's a great question. So we did not begin by looking at thermal expansion coefficient, but scared is not a that makes sense. So we began this research by first looking at the terrestrial champions, because perovskites have been pretty well studied, and they've been innovated for a lot for the past like 10 or 15 years. So we wanted to start instead with the terrestrial state of the art, test that, and then iterate and see how does this perform as we send it through these space qualifications, or space simulations. So my perspective has been to take an accepted device architecture and send it through different environmental characteristics. So first I would send it through thermal cycling, then we will expose it to radiation. Radiation is really one of a greater concern than the thermal expansion. And then we'll take a look at atomic oxide and see how does it perform with that. And on each of these environmental exposures, we're kind of doing a pass fail. I have a remaining factor that I'm looking for in these devices. And if it passes, we say, thank goodness, and go on to the next one. But we are anticipating at some point, there's gonna be an environmental exposure that's really gonna, gut the performance. And that's what we're gonna engineer for, and then we'll check it across the board and see, okay, this really improved our radiation hardness, but what did this do for our thermal cycling performance, or can this stand up to vacuum? So that's the approach we've been taking. That's a great question.
Thank you.
Okay, so before we go on to the next question, I just wanted to say one quick organizational thing, which is that we haven't arranged meetings with Lyndsey because to avoid Zoom fatigue, but she has kindly agreed to meet with people one-on-one if you want to follow up and talk a bit more. So reach out to her, and if you have trouble finding her, I can help connect you with her. Okay, with that said, let's go to the next question. So Aina, you're next.
Thanks. Great talk, Lyndsey. Question about your first bullet here. Is the way to interpret this that basically the perovskite's doing pretty well in space, like the absorber itself is remaining stable, but probably your interfaces are starting to degrade, and that's what's leading to your shunt and series resistance issues?
Absolutely. The absorber layer is standing up to these environments pretty well. It's our transport layers that are degrading and introducing some parasitic resistance within the cell. So we need to get those transport layers that are more robust to vacuum and thermal stress. And then we think we'll see, we can maintain that fill factor during these exposures.
Do you have the capacity to take the samples that degraded in space versus not in space and do something like SIMS all the way through them to look at the different ways that things diffused through interlayers?
That's been posing to be a little challenging, but we're ready to try to attempt something like that. The challenge is that we have this methylammonium lead iodide on a glass substrate encapsulated with this 2-part silicone and then capped by another glass substrate. So if we're having, how do you take it apart? And then we're looking for any analyses first that were not destructive. And now we're ready to destroy it, but it's going to be difficult to separate it. So it would be my dream that there are more things that could analyze this film by going through a layer of glass and ideally a silicone encapsulant, and we haven't been able to find those types of analyses yet.
There's a tool that Hariba has. It's called a glow discharge OES, where they it's like SIMS, but it goes a lot faster and through thicker layers. It has to be like built for the elements that you're looking at, but they do work with people. It might be worth looking into.
Yeah, that was a glow discharge SES.
OES, sorry.
OES.
Yeah, it's a GD-OES, which has been unfortunate, but.
Thank you. I'm absolutely going to look into it. That's what we need.
Okay, so next, maybe Walter, do you want to go next?
Very nice talk. Interesting to hear what's going to happen with these perovskite in space, and you know, interesting that they hold up even better in space, which maybe suggests it's the water and the environment here that kills them, right? But I had a question about these metal oxide layers. What are your, I think they were used as whole transport layers, right? So what are your requirements on band alignment for these metal oxide layers, and why did you pick the ones you picked?
Yes, so band alignment is going to be a challenge, and we're thinking copper oxide is going to be a whole transport layer that we're really kind of considering moving forward. We also anticipate that we're probably going to sacrifice a bit on the efficiency, side of things as we integrate, some of these whole transport layers that are not as optimal as something like Spiro. But we do also think that's a sacrifice worth having if we can get that remaining factor. So beginning of life efficiency will likely decline, but we think end of life efficiency will see a less degradation over the course. Does that fully, excuse me, does that fully answer your question?
Well, I was wondering, does the oxide have to be like a P-type dopable or a P-type oxide, or can it be an N-type oxide? And does it have to have a high work function or a low work function, or?
Yeah, I actually can't comment too much about work functions off the top of my head, but we will need a P type, like a P plus oxide and a N type oxide on either side of this perovskite to get our band alignments working. Some people have been making whole transport layer free perovskite devices, and they're really just relying on their electron transport layer. If you have one layer blocking the flow, they're kind of operating under that. So that's something we could explore, but we haven't looked at that path yet.
Okay, thank you. So well, maybe I should leave my other questions for another time, let other people ask questions.
Okay, so before we move on to the next question, I just realized I have one more organizational thing to mention. Lyndsey is going to be here later this afternoon for an event organized by our graduate student organization, PERMS. This event is only for students and postdocs, but if you're interested in it, you've probably already received information about it. And again, if you haven't, feel free to shoot me an email and I can tell you how to attend that. And with that, let's go on to the next question, which I'll call on Jesse now.
Oh, yeah, thanks. So I just had a kind of a crazy idea. So I don't know too much about space stuff, but I've seen the movies Apollo 13 and The Martian. And in both of those, the thing that saved them was the ability to kind of jury rig things. One actually being real, while they're in space when things go wrong. And so I was wondering, with these perovskite solar cells, they're the fabrication is fairly straightforward. Is there any idea that you could bring the precursor materials up into space with you, and then say if something happens, the solar cell breaks or degrades, or you could actually fabricate new ones in space?
Yes, and that is a great crazy idea, and that's something that we're working towards also. So we really think, you nailed it. Well done. That's the direction that this work is going, is towards in-space manufacture, and that's because of perovskite's ease of manufacturability, that they are vapor processable. And if you take a look and say, well, we more or less, you could kind of work in an evaporator on the moon or in orbit, right? And then you just need to bring up your precursors. So that's something that we're looking at. That also makes the the metal oxides even more enticing because that's something that can probably be evaporated and not something that's relying on spin cast. So really another, overarching constraint in this project is something that can be compatible with in-space manufacturing techniques. And so roll-to-roll processing or vapor deposition or something like that. So yeah, that's exactly the direction that we're headed with this.
Cool.
Okay, so Kathy, do you want to go next?
Yeah, in one of your slides on the thermal vacuum tests, you actually had a couple of samples that improved with the tests, and I just wondered if you could comment on that.
Absolutely. I know exactly which ones you're talking about. Let me click on through here. This one. Yes. So on this thermal vacuum stability test, each bar on these bar graphs is a distinct sample. And our short circuit current is really the one that looks like it's improving. So being that the short circuit current that we're observing is increasing with the sample numbers, we think that this is more an indication that our solar simulator was drifting over the course of the measurement. So we think the applied wattage of the spectrum was increasing slightly, and that the amount of incident light would correlate directly with an increase of short circuit current. So we will take that short circuit current increase with a grain of salt, but our open circuit voltage and fill factor would not be affected by that slight walk in a solar simulator over the course of the measurement. So it doesn't negate the validity of this data, but we think that's why we're observing that little increase is the solar simulator creep.
Okay, thanks.
Yeah.
I have to do that at least once, talk while I'm muted. Yeah, well, if there are no further questions, perhaps this would be a good place to, I guess there is a question though, and we do have a couple of minutes, so maybe I'll let Walter ask that one more question. Go ahead, Walter, you can ask that last question.
Unmute myself, sorry.
Oh.
So in your tandem solar cells, you have this recombination layer. I always thought the recombination is what you want to avoid at all costs in a solar cell. So what's the role of that recombination layer, and what does it do, and what is it made of?
Yes, good question. So recombination layers, you're right. Ideally in a solar cell, that's not the goal. You're trying to avoid it, but it's found to be better for your overall device performance if you can make a region for that and not have recombination, throughout the defects in your solar cell. So I am less aware of what material that would be in a perovskite tandem. I haven't worked in that material space yet, but the challenge becomes it will depend on whether or not you're how many terminals you're going to have on your tandems. If you just have a tandem device that's two solar cells brought in proximity together, or if you're going to have them kind of sharing a terminal. So you'd have to consider your band alignment there, and something that's good for capturing those transport layers. And I'm not sure offhand what the best material would be.
Mm-hmm. Okay, thank you.
Thanks.
Okay, so we're going to have to leave it here, but we definitely have to have you come back and in person to tell us about what you find with the metal oxides and
yes.
With your next payload. So we look forward to that. And thank you very much. And
thank you. Thank you all for having me.
But we'll try and show our appreciation.
Thank you. This was a lot of fun. Thanks for having me.